Hey everybody, it's Paul Lake here, your personal physics pal, with another physics problem solved where I work out a typical physics homework problem all the way through to the answer with lots of explanations, so you get a good look at an example problem. This is a problem that was brought to me by one of my tutoring students. This was a homework problem that she had. So, hey, if you need a tutor, look in the description. There's a way of getting in touch with me there if you'd like a tutor. Now, before we begin, here's what you need to know first. Have you heard of angular momentum? If you haven't, this isn't the problem for you. So, because this is an angular momentum problem. We are going to conserve angular momentum, although this problem it's kind of strange. And you need to understand how to calculate what is rotational inertia. Sometimes it's called the moment of inertia, and particularly for disks, we're going to be we're going to be dealing with disks here. In fact, so let's read through the problem. And after we read through the problem, pause the video and try to work it out yourself. And then as you get stuck, or if you need a little help, just hit play. And then compare your answers with mine, and you'll see how you do. Okay, let's get started. So we have a 5.7 gram quarter rotates like a wheel about its center at 6 revolutions per second. The quarter's diameter is 2.4 centimeters. If all the quarter's angular momentum is transferred to a dime, how fast does the dime rotate? And then the mass of the dime is given, and the diameter of the dime is given. So the way I like to solve problems is I use given, find, and solve. So what's given in here? Well, we've got a quarter, and I've got a dime. And so I'll just use Q and D. Now the quarter, the mass of the quarter is 5.7 grams. And now what I like to do is, if they give me a diameter, I always look, a diameter. I don't like to use diameters. So right away, in terms of what's given, I do a little calculation. What's the radius of the quarter? Because almost everything's based on a radius. Well, 2.4 divided by 2 is 1.2 centimeters, right? If the diameter is 2.4, then the radius will be 1.2, or half of that. Let's see. And it's rotating about like a wheel about its center, like around like that, with an angular velocity of, we use omega for that, of 6 revolutions per second. And then now the dime, we know that the mass of the dime is equal to 2.3 grams. And then the diameter, well, what's half of 1.8 is 0.9. So the radius of the dime is equal to 0.9 centimeters. And so what we're going to do is we're going to transfer all of the angular momentum, which we use in L, from the quarter to the dime. So we're basically the way this problem probably should have been phrased. And again, I'm using homework problems that my students are given, so that's why I'm sticking with that. But how fast would the dime be rotating if it had the same angular momentum as the quarter? That probably would have been an easier way. I don't know how you would transfer all of the angular momentum from the quarter to the dime. Maybe there's some contraption that can do that. But this is the way the problem was phrased. So we want to really find the angular velocity of the dime if the angular momentum of the dime was the same as the angular momentum of the quarter. Okay, so let's solve it. Okay, well, I'm going to start with this, because that'll have it'll have what I want to find in it. The angular momentum of the quarter is equal to the angular momentum of the dime. Now the quarter, well, one thing you have to know about angular momentum is equal to the rotational inertia times the angular velocity. Now, this is kind of interesting, right? Yeah, you've probably already had linear momentum, I hope. Like linear momentum equals mass times velocity, right? Well, angular momentum, we use a capital L for it. We're going to use analogous variables here. Instead of velocity, we're going to use angular velocity. And then m, what's equivalent to mass for a rotating object is rotational inertia. Sometimes with my students, I would call it rotational mass. It's kind of the equivalent of mass. It includes mass in it, as we're going to see, but it's for rotating objects. And okay, so, well, let's get to that. We know that L is equal to I omega, so this is I for the quarter times omega for the quarter is equal to I for the dime times omega for the dime, the angular velocity for the dime. All right, well, these are disks, and you have to look this up. And hopefully you've been taught this in your class. But for a disk, if you have any kind of rotating disk or cylinder, and it's rotating about its center, and it's solid all the way through, and it's uniform density and everything's nice and symmetrical. The rotational inertia of this is half the mass of the disk times the radius of the disk squared. And this can be derived using calculus and so on, but you have to, for the purposes of this problem, you probably need to just look this up. And so we're going to use that. For the rotational inertia for the quarter is 1/2 the mass of the quarter times the radius of the quarter squared times omega of the quarter, and this is equal to 1/2 the mass of the dime times the radius of the dime squared times angular velocity of the dime. Well, what do we know? We know the masses, and we know the radii for the quarter and the dime. And we know what the angular velocity of the quarter is. So the only thing, what I'm trying to find is here. So all I have to do is solve for this. So this is a pretty simple problem, actually. So the angular velocity for the dime, well, notice that the 1/2 is on both sides, so I'm just going to cancel it out. So this is the mass of the quarter times the radius of the quarter squared times angular velocity of the quarter divided by the mass of the dime times the radius of the dime squared. Okay. And so now I know everything. I can just plug those values in. Now, quite often, in a lot of the problems I solve, I like to go right from grams to kilograms and right from centimeters to meters and so on. But because I could see that we're comparing two things, the dime and the quarter, all those kinds of non-standard units, it's grams instead of kilograms and so on, it's going to cancel out. So I just left them as grams. So the mass of the quarter is 5.7 grams. The radius of the quarter is 1.2 centimeters, and I have to remember to square that. And then the angular velocity of that is 6 revolutions per second. And now we're going to divide by the mass of the dime, which is given to be 2.3 grams. And then we have the radius of the dime squared. And when we do that, we get our answer. This is what we were trying to find. The angular velocity of the dime would have to be, if you round it off to two significant figures, you're going to get 26 revolutions per second when you plug all that into your calculator. And notice that, and I always go back, grams cancels grams, centimeter squared cancels the centimeter squared. We're left with revolutions per second. That's what we wanted. And so there we go. So a pretty simple problem. But, hey, it's good to do simple problems before you do more complicated ones. And so, hey, If you found this helpful, please give the video a like and subscribe to my channel. And that'll inspire me to make more of these. And also in the description, there's a link to a document where I've listed all my videos that I'm making. Like this is Google Doc, and I'm listing all those videos. So maybe you can find the one that'll be the most helpful to you. All right. Well, thank you for your attention. And until next time, may the net force be with you.